Hi there, and basically our new topic that we're going to be learning about is something called equilibrium. But we're going to go back a step from equilibrium and we're going to first remind ourselves about some reversible reactions. You might have seen some of these before. You might have seen at National 5 that water can dissociate into its ions, H plus and OH minus, and that is a reversible reaction. You might have also heard the term equilibrium mentioned then but not explained. We're going to work out what it is today. Another reversible reaction you might have seen before as well is when you're making an ester. And remember we said that you have a carboxylic acid and an alcohol and they react together to form an ester and water. However, when you add water to an ester, it's reversible, so it goes back into the carboxylic acid and the alcohol. And actually, when you form an ester, you don't 100% form the ester, and that's it. You always do have a mixture of the ester and also the carboxylic acid and the alcohol, and that is because it's a reversible reaction under something called equilibrium. And we're going to have a look at what a reversible reaction means, and then we're going to go on to equilibrium as the next step. So we said some chemical reactions can be considered to be reversible, and that's where the products are able to change back into the reactants. Now most reactions are not reversible, but there's going to be a lot that are. How easy it is to reverse will depend on the activation energy. So if we think about a wee graph, I'll just draw one up at the top. If we think about a wee graph, the potential energy diagrams, if you have one that looks like that, then that's going to be quite easy because the activation energy, the size of the kind of hump, is low. Whereas if we had this graph, then that's not going to be very easy. So that's not going to be likely to be a reversible reaction. It's because there's a lot more energy needed to go back to the products. In reversible reactions, a 100% yield is never going to be possible as the reverse reaction begins as soon as the product has been made. So actually, as soon as you've even made your product, it's already turning back into the reactants. So when we made our ester in that experiment, some of it was already turning into the carboxylic acid and the alcohol. And you might have been able to smell that as well. If you had smelt the ester, you might have been able to smell a wee bit of the carboxylic acid in there as well. We didn't really look at that though. So let's move on to actual equilibrium and let's find out what it means and what it means for the chemical reactions. When you have a reversible reaction happen in a closed system, now that means, for instance, if you imagine a test tube or a boiling tube with a stopper on top, a chemical reaction happening in that. Because that's sealed, that means that's called a closed system. An open system would be where it's not stoppered off and it can react with all the things in the environment. If it's closed though, that means that it's closed to the environment, it's got a stopper or it's a kind of sealed container. An equilibrium will exist. So there will always be an equilibrium if it's going to be a reversible reaction in a kind of stoppered, sealed system. That would happen inside a reaction vessel or a tank with a closed lid. So let's have a look at what this means. So it's the ratio of products to reactants to products. There'll always be a kind of situation where you might have more products or more reactants, and we're going to look at this as we go on through the next series of lessons. It's talked about as having a position, and this position can move towards the left, which is the reactant side. Okay, so if it was to move towards the left, then the concentration of the reactant would increase. You'd have more reactants, you would products. But if it moved to the right, that'd be moving towards the product side. The concentration of the product increases if you do that. So if you even just think of the chemical reaction reactants, you could call them A and B. Products, we'll call them C and D. And actually what that means is if it's moving towards the left, then you're going to have more of A and B than C and D. Or if it's moving towards the products, then you're going to have more of C and D than A and B. I'm also going to talk about equilibrium has a special kind of arrow to tell you that it's a reversible reaction. So a reversible reaction would have this arrow here. So that kind of double kind of headed arrow, that means it's a reversible reaction. So technically you should be writing A plus B with this double arrow, C plus D. So if you're ever talking about a reaction that's under equilibrium, that's in a closed system, that there's going to be an equilibrium set up, and it's going to have that strange reversible reaction arrow. So you'll never forget that. So let's talk about what dynamic equilibrium is. Now, this state of equilibrium is reached when the rate of the forward reaction equals the rate of the reverse reaction. So what that means is that the rate of the forward reaction is the same as the reverse reaction. It means that they are both at the same speed. Okay, so none of them are having faster than slower. If you're this doesn't affect the concentrations, so it might lie to one side, but the rate at which the products and the reactants are actually formed is going to be equal. So it's known as a dynamic equilibrium, as the reactions don't stop. They're actually constantly occurring, and we're going to see a reaction that's actually at equilibrium, and you'll be able to see that it looks as if it's stopped, but actually what is happening is that the forward and reverse reactions are happening all the time. You just don't, it doesn't look as if anything's happening. So you might have the reactants turn into the products, but then those formed products are always turning back into reactants. So it's a wee bit like a kind of cycle that just keeps on going. So this is what would actually happen at equilibrium in terms of the reaction rate. And what is actually happening is that you can see the forward reaction rate is decreasing until it reaches this point in the equilibrium, and the backward reaction is increasing. Now the reason that that's happened is because the reactants, so the reactants would be up here, and these are the products. Well, the reactants are going to get used up because you'll be starting with the reactants, and as they're used up, the kind of rate would decrease. But the products, going back to the reactants, they would actually increase because the products are being made, but then that reaction is getting faster because it is going back to the products, the reactants. So that's kind of starting a cycle almost. And at this point here, which I'm going to mark point X, because that line is flat, and also the forward reaction rate and the backward reaction rate are equal at that point, and all the points after this, like along here, then that is where equilibrium is set up, and it's because those rates are the same. Now, it doesn't mean that the concentrations may necessarily be the same as we're going to look at, but it's just that the rate of the reactions between the forward rate and the reverse rate are the same. Hopefully that makes sense. If you need to pause at all, then you can stop here and try and get your head around this. It is quite tricky, so it might take a wee few listening throughs just to make sense of all this. But essentially all that's happening is that the main thing is that the forward reaction and backward reaction are the same, and when they are the same, that is when you have equilibrium set up. At equilibrium, as well as the rates being the same, the concentrations of the products and the reactants are constant. Now that doesn't mean the same, that just means that they're going to not change, okay? So not going to be the same as each other, but they're just not going to change. So these two definitions must be met for an equilibrium to exist. So the rates need to be the same, and the concentrations need to remain constant. And I'm going to show you what that would look like on a graph just now. What you can see is that this is the concentrations, this is the reactants, so we'll put a wee R there, and we'll put a P down here. As you can see, the reactants are being used up, so their concentration decreases, until you get to a point where it kind of levels off. The products are being made, so their concentrations are going to increase, until you get to this point where it levels off up here. Now you can see that they're going flat. On that graph, it looks as if it's flat. So that is where equilibrium is set up. Equilibrium is set up at this point here. Oops, that's a wee bit messy. I'll just make that neater. Equilibrium. And the reason equilibrium is set up at that point is because that is when the lines for the products and reactants concentration goes flat. and that tells you that they are not changing. It tells you that they're constant, and we said that was the point that equilibrium was set up. So the concentrations of the reactants and products will be constant when the mixture is at a dynamic equilibrium. So it might look as if the reaction has stopped because the concentrations are not changing. However, the reaction has not stopped. They're constantly, the products are being changed into reactants, and the reactants are being changed into products. And the rate that they're being used up, they're being replaced at the same rate. So it looks as if it's stopped, but the reaction is constantly going at the same time. We're going to have a wee look at an experiment, but basically what you'll see in the experiment, I'll actually show you me doing it. We're going to add some iodine into the Ki, which is potassium iodide. So add some iodine into this, and then we'll add some high cyclohexane as well. That's in test tube A, and then we're obviously going to stopper it. We're going to put some potassium iodide into test tube B, and then we're going to put some cyclohexane with some iodine dissolved into it in the top. And what you should see is that the bottom layer for this test tube A has a nice, when it's dissolved in potassium iodide, it produces a nice yellowy colour. When it's in the cyclohexane, the iodine, it produces a nice purpley colour. And what you'll see what happens when we shake this up. And what should happen is we should have an equilibrium set up, and I'm going to show how this is proven by the experiment. Okay, at this point, if you have any questions, you can ask your teacher. Obviously, there's going to be questions coming up as well, so just make sure that you understand them, and if you need any help, get in touch with your teacher. Thank you. Okay, so this is an experiment that shows you that we can set up equilibrium, and it doesn't matter where we're going to dissolve the iodine. It will still form the same equilibrium mixture, which I'll mention later on. So what I'm going to do is, in my first test tube, I'm going to put some cyclohexane in. I'll put 2 droppers full. And then what I'm going to do is I'm going to add a little bit of iodine crystals. As you can see, that kind of starts to turn a nice purpley colour. What we'll do then is we'll get the other dropper and we'll add in some potassium iodide. Do 2 droppers full. And what we should be able to see there is we set up 2 layers. We've got our cyclohexane dissolved in the top layer, cyclohexane top layer with iodine dissolved, and then we've got some potassium iodide here as well. Okay, what I'm going to do this time is I'm going to add the potassium iodide first, and I'm going to dissolve the iodine in that. So we'll just add another few crystals of iodine. Get that nice and dissolved. You can see that's kind of turning a nice kind of yellowy colour. And what we'll do is we'll add some cyclohexane on top of that, and then we'll put the stoppers on both. And as you can see, because there's no iodine dissolved in this top layer of cyclohexane, it's forming this nice clear colourless layer. Okay, so what we're going to do is I'm going to talk about the equilibrium that's set up between these 2 layers. Iodine can dissolve in potassium iodide, which is this side here, and it can also dissolve in the cyclohexane, which is this side here. There's an equilibrium set up between these 2 layers because the layers themselves don't mix. So iodine has to kind of go between the 2 layers and in a kind of equilibrium. So what you should see is what happens when I shake these 2 up. So I'm going to shake them up. Let off the pressure a wee bit. Shake back in, let off any wee pressure. Sometimes you have to do this because a pressure of gas is built up. And I'm just going to let them settle for a wee second. I think we need to leave them a wee bit longer. No, actually we're fine. And what you can see is that both of these now have some iodine dissolved in the top layer, that's the cyclohexane, and they also have some iodine dissolved in the bottom layer, that's giving it that yellowy colour. And the reason that they both dissolve is because it doesn't matter which way you shake them, the equilibrium means that these will be shared amongst those two layers, like that. And it doesn't matter which way you start, when you shake them up, they're all mixing, and then they go into this equilibrium mixture that we've got shown here. Okay. And as we can see from that experiment, this would have been the results we've got. It doesn't matter which way you add the iodine, and then you add the cyclohexane, and you add the potassium iodide. When you mix them up, they will always create the same equilibrium mixture. You will have the iodine distributed over the two layers. Because they don't mix, the iodine has to have an equilibrium set up between it dissolving in the cyclohexane, which is the top layer. Put psi, and then this is the Ki on the bottom. So it has to have an equilibrium set up between those two layers, and actually what you'll find is that the iodine will always be moving between the two in the proportions. So when you shake it up, you just kind of mix it all, but then it settles into that equilibrium. Here's the equilibrium equation for this. So you have I2 dissolved in Ki, and then we've got our reversible arrows, and then this is I2 dissolved in C6H12. That's cyclohexane. And as you can see, it doesn't matter which way that you mix them, whether you put the iodine in potassium iodide first, or if you put it in the cyclohexane first. Whichever way you do it, when you mix it up, it still separates into the same equilibrium. So hopefully that makes sense, and you'll be able to see that okay in the video.